Alright, so here's the screen from the last slide. That shows how when we have an increase in height, we have a decrease in pressure. The kinetic energy stayed constant because the velocity stayed constant. The velocity stayed constant because the area stayed constant. Because the flow rate's the same because we have an incompressible fluid. So follow that logic. Incompressible fluid, constant area, constant velocity because of constant flow rate means constant kinetic energy. So the kinetic energy does not decrease on the way up like you would with a ball that you would throw up. A ball that you throw straight up loses kinetic energy because it gains potential energy. But here, it's not kinetic energy that loses or that drops, it is pressure. Creating a low pressure system here, a high pressure system here, and that creates the force vector from more to less pressure that goes against gravity, thus maintaining the speed. Otherwise, gravity would slow the fluid down, but because the velocity must stay the same because it's incompressible, the force points from high pressure to low pressure. So the summary, just know what's in this box. Height increases, which means potential energy increases, means pressure decreases. And if the height decreases, potential energy decreases, means the pressure increases. Alright, part 2. If I change the area without changing the height, the only way to change the velocity is to change the area. The height's the same, then we have the potential energy is the same, so if I write Bernoulli's equation, then what we see is that the potential energy this time stays the same. Because h1 equals h2, so the height here is the same as the height here. So this is h1, this is h2, they're the same, so we have the same potential energy. Which means the potential energy drops. But what happened to the kinetic energy? Well, here, the kinetic energy increased at point 2. Why? Well, because A is smaller. If A2 is less than A1, then V2 will be greater than V1, as we saw with flow rate. Right? So since the flow rate's constant, the only way to change the velocity is to change the area. And if we do make a smaller area, we have a larger velocity. Therefore, kinetic energy increases. What does that say? Well, if this goes up, this goes down. Pressure increases. There it is. So here's the other box. This is so simple, guys. It's amazing. So in general, when a fluid goes faster, it has less pressure. If a fluid goes slower, it has more pressure. So be careful. You might ask yourself, wait a second, but if I have a hose of water and the hose of water is spraying somebody and that somehow goes faster, isn't it going to exert more pressure on them? Yes, it will. A faster fluid will exert more pressure on an external object. However, that is not what this pressure is in this equation. This is fluid in a closed pipe. Remember, this fluid is pushing on itself only, and the sides of the pipe, of course. So this is hydrostatic or gauge pressure. Technically, it's the total pressure in a fluid caused by the molecules all pushing on themselves. So this is different from if this was to leave the pipe, not be a closed system, and push on some external object. That's not the pressure this is talking about. This is the force that the fluid pushes on itself. So if I have a high pressure system here because it's slower here, and I have a low pressure system here because it's faster here, then guess what? I get a force vector from high pressure to low pressure, which means, of course, which velocity would have to be bigger? Well, if the force is pushing this way, if more molecules are pushing than these molecules are pushing, it's going to speed up the molecules. Isn't that amazing? Let's compute an acceleration from here to here. So our pressure differential actually causes the speed change. So let's summarize. This is called the Bernoulli effect. And the Bernoulli effect is faster means less pressure, slower means more pressure. We'll do some examples in class, but I just want you guys to have the notes here. And of course, let's add what we did on the previous slide, which is this. I'm going to summarize this in nice, neat little words, where if it goes higher in height, meaning higher in height, higher h, right? It's going to be what? Well, higher means less pressure. Slower and lower in height, so less height. So if it goes down, it's going to be more pressure. So here's the whole point. Kinetic energy and potential energy no longer exchange with one another. Isn't that cool? When you throw a ball upwards, a projectile loses kinetic energy on the way up, gains kinetic energy on the way down. If I have a fluid flowing uphill, it does not lose kinetic energy necessarily. It can, but the only way to change the velocity is to change the area. Isn't that cool? So instead, what we have is kinetic energy exchanging with pressure, or potential energy exchanging with pressure. So it's all about conservation of energy, and in the end, honestly guys, all you need to know is what's in this box. But you should know where it comes from, because you might get confused and you might forget it. It's always nice to have the foundation. Yay. Thank you guys. Have a beautiful weekend. I'll see you on Monday.